Well, students, we have learned some quadrature rules, and also we have learned two methods of deriving quadrature rules. One is the direct method and another one is the method of undetermined coefficients. In the method of undetermined coefficients, we demanded certain conditions, and using these conditions, we obtained a class of quadrature rules which are exact if the integrand is a polynomial of degree n whenever the quadrature rule involves n plus 1 weights, right? In this lecture, we will see that we can use the method of undetermined coefficients with more stronger conditions and thereby get quadrature rules that are exact for polynomials of degree 2n plus 1. When the quadrature rule involves n plus 1 weights, such quadrature rules are called Gaussian Quadrature rules. Let us see what is the key idea in this improvement. If you recall, in general, we fix the nodes in our formula. That is, given n, and also we are provided with the nodes x0, x1 up to xn. Therefore, in the quadrature rule, we have no freedom to change the nodes. Nodes are already given to us. That is what we have seen so far in the quadrature rules that we have developed. Now what we will do is, you give me only n. This is the only input that you take, whereas the nodes as well as the weights are not fixed for us. But we have to find all these parameters as the part of the derivation of the quadrature rule. That is the idea. Therefore, how many unknowns are there in the general form of the quadrature rule? Let us see. We have weights W0, W1 up to Wn, which were unknown in our previous method also. Now what we do is, we also consider the nodes as unknowns. Previously, we fixed them, but now we will consider them also as unknowns. Therefore, totally we have 2n plus 2 unknowns. To eliminate 2n plus 2 unknowns, what is the condition that we have to assume in the method of undetermined coefficients? If you recall, in the last class, we have introduced a method called method of undetermined coefficients, where to eliminate only the weights, whereas the nodes are given to us, we assume that the quadrature formula is exact for polynomials of degree n. Because if you have polynomial of degree less than or equal to n, then you have n plus 1 generating elements, namely 1, x, x square up to xn, right? So you have n plus 1 elements and you had n plus 1 unknowns, and that is why we have assumed that the quadrature rule is exact for polynomials of degree less than or equal to n. Now we have 2n plus 2 unknowns. Therefore, what should be the degree of the polynomial that we should assume that the quadrature rule is exact? It should be 1 less. Therefore, it should be 2n plus 1. So that if you start from x to the power of 0 up to you go to x to the power of 2n plus 1, you have totally 2n plus 2 constraints to be satisfied, right? And you have 2n plus 2 unknowns are there. Therefore, you have scope to obtain the weights as well as the nodes by imposing these conditions. So we have to now impose that the quadrature rule is exact for polynomials of degree less than or equal to 2n plus 1. Let us make it more precise. We will now look for a quadrature rule of the form W0 f of x0 plus W1 f of x1 plus dash 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 plus Wn f of xn. Remember, this general form is the same as what we considered in the previous classes also. The general form has no change in it, but what is the change? Now we will not provide the nodes. The nodes will also be obtained as the part of the method of undetermined coefficients. That is the new idea in the Gaussian rule. So let us consider the quadrature formula in this form such that this quadrature rule is exact for polynomials of degree less than or equal to n was our previous idea. Now we will demand that this quadrature rule is exact for polynomials of degree less than or equal to 2n plus 1. That is the new condition that will give rise to another class of quadrature rules called the Gaussian quadrature rules. Okay, so this can be achieved by choosing n plus 1 nodes as well as weights appropriately. Okay, nodes are not given to us, but we have to find the nodes as the part of the method, as I told you. So that is the key idea of Gaussian quadrature rules. We will derive the Gaussian quadrature rules only for the integrals over the interval -1 to 1. Why we are restricting only to -1 to 1 is, well, this is for making the derivations more simple. Once we make the formula for the integral over -1 to 1, then we can use a simple change of variable to go from -1 to 1 to a to b. Thereby, we can achieve formula for any integral a to b f of x dx. That is the idea. So first we will see how to develop the Gaussian quadrature rules for this particular case, and then we will also provide what is this change of variable that takes the interval -1, 1 to ab. That's very elementary. We all know this. So what are the things to be chosen as a part of the method? They are not given to us, but we have to find. Probably the correct word could be to be found as the part of the method of undetermined coefficients. Here they are the weights as well as the nodes. So these two are to obtain. They are not provided to us. We have to obtain. What is given? Given is only n. Now, what is the condition that we have to impose? We have to impose that the quadrature rule, which in general is approximately equal to, not exactly, but now we have to impose the condition that the quadrature rule is exactly equal whenever f happens to be a polynomial of degree less than or equal to 2n plus 1. So you should try to understand why we are choosing this particular number 2n plus 1, because we have 2n plus 2 unknowns. So we need 2n plus 2 conditions, and therefore, if you impose the degree of the polynomial to be 2n plus 1, then degree 0, 1, 2 up to 2n plus 1 will actually give rise to 2n plus 2 equations to be solved. That is the idea of choosing this number 2n plus 1 as the degree of the polynomial. So the quadrature formula should be exact for all polynomials of degree less than or equal to 2n. And as we have done in the previous case, here also we can break this one single condition into this n plus 2 conditions. That is, the formula is exact for polynomials f of x equal to 1. That gives you one equation. Then f of x equal to x, that gives you another equation, and similarly the other cases. So you will get finally 2n plus 2 equations. By solving the 2n plus 2 equations, you will get n plus 1 weights and n plus 1 set of nodes also. So that is the idea. And once you get the weights and nodes, that will be a quadrature rule called Gaussian quadrature rule with n is equal to whatever the value that you choose. For instance, let us choose n equal to 0 and see how the quadrature rule for n equal to 0 will look like. Now, once you have n equal to 0, remember, this is the general form of the quadrature rule that we always take. And now, since we have taken n equal to 0, this will be simply w naught f of x naught. Remember, in the previous case, for instance, its equivalent in our previous class of quadrature formula is the rectangle rule or the midpoint rule, right? Where we choose x naught by ourselves as either a or b or a plus b by 2 or anything you can choose for that matter. But we choose and fix it and then go to find what is w naught. But here what we do is we will not choose x naught. We will also try to obtain x naught as well as, of course, w naught, such that this quadrature rule is exact for polynomials of degree, how much? Less than or equal to 2n plus 1, right? N is equal to 0, therefore the degree is less than or equal to 1. Therefore, you have to impose the condition when f of x is equal to 1, that is one condition, and f of x equal to x, that is the second condition. Let us see, we will take f of x equal to 1, and that gives us the equation integral minus 1 to 1 dx equal to omega naught. So that is the condition that we are imposing. It should be equal. And similarly, let us put the second condition, integral minus 1 to 1 x dx equal to w naught into x naught. So you can just solve these two equations to get w naught equal to 2, which comes directly here, and put that w naught here and get your x naught value as 0. Therefore, the Gaussian quadrature rule with n equal to 0, that is what we use the notation I g naught of f, is given by 2 times f of x naught. So you just put w naught is equal to 2 and x naught equal to 0. So that's the quadrature rule coming out of this idea when n is equal to 0, and that is the Gaussian quadrature rule for n equal to 0. You have already seen this quadrature rule previously. If you recall, this is nothing but the midpoint rule, right? If you recall, what is midpoint rule? Midpoint rule is nothing but b minus a into f of a plus b by 2. That is the midpoint rule. Here b is 1, a is minus 1. Therefore, b minus a is 2. That is here. And f of a plus b by 2. Again, minus 1 plus 1 by 2 is 0. This is 0 in this particular integral. Well, we will generalize it later. But at this stage, the midpoint of the integral over which we are integrating is 0. And that is what is sitting here. So the Gaussian quadrature rule with n equal to 0 is precisely the midpoint rule. There's nothing else. Let us take up the case when n is equal to 1. Again, the general quadrature rule formula now reduces to w naught f of x naught plus w1 f of x1, where w naught, w1, x naught and x1 are unknown to be obtained now, right? By imposing that the quadrature rule is exact for the polynomials of degree less than or equal to 2n plus 1, right? N is 1, therefore it is 3. So how many conditions we will have here? F of x equal to 1, if you take, you get one equation. F of x is equal to x. F of x equal to x square, and f of x equal to x cube. So these are the conditions we have to impose, and thereby we will get 4 equations. We have 4 unknowns. Therefore, we hope to obtain all these unknowns by solving these 4 equations. If you impose f of x is equal to 1, we get this equation. Then if you take f of x equal to x, you get this equation. If you take f of x equal to x square, you get this equation. Finally, f of x equal to x cube, if you take, you get this equation. Therefore, you have 4 equations. Note that these are nonlinear equations. Hence, you obtain a system of nonlinear equations. Unlike in the previous case, you had system of linear equations. That is because you have fixed this parameter, f of x1, f of x0. All these were fixed because we know the nodes. But now, since nodes are also unknown, in general, if you are working with a nonlinear equation f, then your equations will also become nonlinear, and thereby you land up with solving a system of nonlinear equations. This is not as easy as in the previous case. Well, we get a better quadrature rule by going through the Gaussian idea. However, to obtain the quadrature rule, you have to undergo this difficult step of solving the nonlinear system. In the case of n equal to 1, again, with little effort, you can find it. You can see that the solution of this nonlinear equation is given by W0 is equal to 1, W1 equal to 1, and X0 equal to minus 1 by root 3, and X1 is equal to 1 by root 3. And therefore, the Gaussian quadrature rule with n equal to 1, we use the notation IG1 of f for that, and that is given by f of minus 1 by root 3 plus f of 1 by root 3. That is the formula for the Gaussian quadrature rule with n equal to 1, and that is taken to be the approximate value of the integral minus 1 to 1. Remember, it's not a general case, it is a particular case as far as the interval is concerned. It is integral minus 1 to 1 f of x dx. In the same way, you can go ahead and derive Gaussian quadrature rule for n equal to 2, 3, and so on. As I told, they give rise to more complicated nonlinear equations. I will not ask you to derive Gaussian quadrature rule for n equal to 2 or 3 or something. However, I will just tell you how in general they look like, at least the equations. In general, the quadrature rule for some given n leads to the system of nonlinear equations of this form. Okay, you can just put these values, that is f of x equal to 1, f of x equal to x, and so on. And you can see that finally the system of nonlinear equations will look like this. How you will solve? Well, that is very difficult. So let us just be aware of such things, but we will not go to solve them. Okay, as I told, these are nonlinear equations, and their solvability is not at all obvious, and therefore the discussion is actually out of the scope of our course. But however, n equal to 0 is not very difficult, and n equal to 1 is not very difficult. So we will restrict ourselves to n equal to 0 and n equal to 1 from the examination point of view. Well, so far we have derived Gaussian rule for the integrals over the interval minus 1 to 1. Now let us see how to transform this integral to any interval a to b. Well, that can be achieved by this simple change of variable. X equal to b plus a plus t into b minus a by 2. You can see that whenever t belongs to minus 1 to 1, x will belong to the interval a to b. In particular, if t is equal to minus 1, you can see that x is equal to a. And similarly, if t is 1, we can see x is b. and in between this is just a straight line. Therefore, this is a good change of variable that can be applied to transform the integral from -1 to 1 to the integral a to b. Therefore, you have to keep in mind, if I ask you to obtain an approximation of some integral which is not integrated over -1 to 1, then don't forget to do this change of variable before applying the Gaussian rule. So what you have to do, you want to evaluate integral a to b f of x dx, but Gaussian rule is only given for integral -1 to 1. Therefore, you have to apply Gaussian rule to this integral, not to this integral. Okay, you have to apply Gaussian rule to this integral. You should not forget this. Often students forget and just simply write the Gaussian rule for this and give the answer. That will be wrong. Okay, you have to apply the Gaussian rule for this integral, and then don't forget to also multiply it by b minus a by 2. So you are finally applying Gaussian rule to this integral, not to this integral. Okay, that's wrong. Okay, so this is just a simple technicality you have to keep in mind. Let us go back to our classical case of integrating the function f of x equal to 1 by 1 plus x in the interval 0 to 1. Remember, its exact value is 0.693147. And also remember that the integral is not over the interval -1 to 1. Therefore, you have to first put the change of variable and then apply the Gaussian rule. So the change of variable in this case is given by x equal to t plus 1 by 2 for all t in -1 to 1. And therefore, you actually want to evaluate this integral that can be equivalently written like this. And since this integral is over the interval -1 to 1, Gaussian rule can be applied to this integral, not to the one which you want. Okay, so that you should keep in mind. And now once you know on which integral we have to apply the Gaussian rule, you can go ahead and do that. Remember, f is 1 by 3 plus t, not this one. Okay, so this probably I should have given a different notation. Say g, you have to apply the Gaussian rule for g of t, not for f of t. Okay, so g of t is 1 by 3 plus t. So we have to find the integral -1 to 1 g of x dx, and that is, let us take the Gaussian rule with n equal to 1, and that is given by g of -1 by √3 plus g of 1 by √3. Remember, I have just changed the notation f to g here, and the integrand is 1 by 3 plus t. That is more important. Whether you use the notation g or f is not important. Okay, where the integrand is 1 by 3 plus t. That is more important. So once you are clear about what is your integrand, you can just apply the Gaussian rule on it, and the answer that you get from the Gaussian rule with n equal to 1 is 0.692308. And the mathematical error in this case can be explicitly found because we also know the exact value of this integral. And this is in fact little better than even the Simpson's rule, if you recall. Remember, Simpson's rule was derived by imposing the condition that it is exact for polynomials of degree less than or equal to 2. But here in the Gaussian quadrature rule with n equal to 1, we obtained the formula by imposing the condition that it is exact for polynomials of degree less than or equal to 3. That doesn't mean that we will always get better accuracy for any integral that we evaluate using Gaussian quadrature, but it's basically it's an improvised method than the Simpson's method. That's all we can say, but it's not necessary always that Gaussian quadrature rule should give better accuracy than the other methods. You cannot say like that in general. Next, let us establish the upper bound for the mathematical error involved in the Gaussian quadrature rule. Assume that f is continuous in an interval AB and n greater than or equal to 1 is given to us, then the absolute mathematical error involved in the Gaussian quadrature rule satisfies this inequality, where rho is defined as the infimum of all polynomials of degree less than or equal to 2n plus 1 over the infinite norm of the difference between f minus that polynomial. So this is also called min-max error of order 2n plus 1 for the function f on the interval AB. Let us try to establish this estimate. Let us assume that the infimum, that is this infimum, is achieved for a polynomial q star 2n plus 1 of x. It means what? Infinite norm of the difference between f and q 2n plus 1 star is precisely the infimum, right? And that infimum is actually denoted by rho 2n plus 1 of f in the statement of our theorem. Therefore, the infinite norm of the difference between f and q star 2n plus 1 is precisely your min-max error. Now what we will do is we can write the mathematical error involved in the Gaussian quadrature rule when compared to f as, you just retain this as it is, and then you subtract this number from this. Why these two are equal? Well, if you recall, Gaussian quadrature rule is exact for polynomials of degree less than or equal to, if you recall, it is 2n plus 1, right? And your q star 2n plus 1 is some polynomial of degree less than or equal to 2n plus 1, right? Basically, it is a polynomial of degree something less than or equal to 2n plus 1. Therefore, if you plug in q star as the integrand and use Gaussian quadrature for that, you will in fact get the exact value. Therefore, the mathematical error involved in the Gaussian quadrature of q star as the integrand is actually 0. In fact, the mathematical error for any polynomial of degree less than or equal to 2n plus 1 will be 0, right? So I'm precisely subtracting 0 from this number, and therefore I can comfortably write MEN of f equal to MEN of f minus 0. Now you use the additive property of the mathematical error when applied to two continuous functions on the closed and bounded interval AB. When you use that, this can be written as this, right? In fact, this minus can also go in because you can also check that the scalar multiple also holds. Therefore, I can write MEN of f as MEN of f minus q star 2n plus 1. Now, what I'm doing, I'm just applying the definition of the mathematical error. Definition of the mathematical error is nothing but the exact value minus the approximate value. Remember, this is nothing specific to Gaussian quadrature. It is just the general form of any quadrature rule that we make. But here, what is specific for Gaussian quadrature is that it is exact for polynomials of 2n plus 1. Okay, and this is where we are, more specific to the Gaussian quadrature. Otherwise, all these steps will go through for any quadrature rule that we do. Okay, but this polynomial degree should be chosen appropriately depending on what kind of quadrature rule we use. Well, now you take modulus on both sides. You can see that modulus MEN of f is equal to, that is modulus of this is equal to modulus of this. Then you take less than or equal to and take the modulus inside this and make a plus here. And further it is less than or equal to, you take the modulus inside the integral and remove this out by taking the infinite norm, right? Then what happens? This will be equal to infinite norm of f minus q star to n plus 1, right? And what remains is integral a to b dx, right? No, sorry, this is less than or equal to. So once that infinite norm comes out, you have integral a to b dx, and that is nothing but b minus a. And that is the first term. And what is the second term? Second term, again, you take this modulus, dominate this by its infinite norm. Therefore, it is f minus q star to n plus 1 infinite norm. And what remains is sigma j equal to 0 to n mod wj, right? That is, this term remains. This term comes out with infinite norm. And this term, when you dominate by infinite norm, then it comes out of the summation. And that is what I'm writing as the right-hand side here. Now, you can see that the second term is nothing but b minus a. Okay. If you sum all the weights, you will get back the length of the interval on which you are performing the integral. Okay, so I leave it to you to check this. This property holds for any quadrature rule, not only for Gaussian quadrature. It's not very difficult to prove this. So once you use this, you have already b minus a, and this is nothing but b minus a. Therefore, you have 2b minus a into this now, and this is your rho 2n plus 1 of f, right? And there are 2 times b minus a, and this is precisely what we want to prove as the estimate for our mathematical error involved in the Gaussian quadrature rule. And this completes the proof.